The moment your garbage truck turns the corner, your trash seems to vanish, but it has only begun a carefully managed journey through one of the largest machines your community operates. A modern landfill is not simply a hole where waste is buried. It is a layered structure of clay, plastic, gravel, pipes, pumps, wells, sensors, and compacted soil. And everything inside it is moving. Water tries to move downward, gas tries to move upward and sideways. The waste itself slowly settles under its own weight. If engineers lose control of any one of those movements, a quiet disposal site can become a long-term problem. So let us follow one ordinary bag from the collection truck to its final resting place and see how this hidden system really works. In many cities, the first stop is not the landfill at all. It is a transfer station. Collection trucks are designed for neighborhood streets, not for long highway journeys. At the station, several local loads can be combined into a larger truck, rail car, or container. That reduces the number of long-distance trips to a disposal site that may be many miles away. When the load finally reaches the landfill, the truck passes over a scale. Its weight is recorded on the way in and again on the way out. The difference tells the operator how much material arrived. That number matters because a landfill sells a very unusual product, a limited amount of three-dimensional space known as airspace. Every loose box, cushion, and plastic container consumes some of that capacity. The entire daily operation is built around using that space efficiently. The truck is directed to the working phase, the small active area where waste is being placed that day. Keeping this area limited helps operators control blowing litter, birds, insects, odors, and vehicle traffic. The truck unloads and enormous compactors take over. These machines are not ordinary bulldozers. Their heavy steel wheels are fitted with teeth that crush, spread, and press the waste into dense layers. Compaction does two jobs at once. It squeezes more years of useful capacity from the site, and it creates a more stable mass. But it also begins the third movement engineers must watch: settlement. Cardboard collapses. Organic material decomposes. Air pockets close. A surface that looked level when it was built can sink unevenly later. Pipes, roads, drainage channels, and the final cover must all be designed with that continuing movement in mind. At the end of the operating day, exposed waste is covered. Under United States federal rules, 6 inches of earth is the standard daily cover, although approved alternative materials can be used. This layer is not the permanent cap. It is more like closing the lid each night. It reduces odors, discourages pests, limits litter, and separates today's work from tomorrow's layer. Now imagine looking below our bag. Long before the first truck entered this part of the site, crews prepared the ground as carefully as they might prepare a reservoir. Federal criteria for new municipal solid waste landfill units generally require either a protective performance standard or a composite liner system. A common composite design places a flexible synthetic membrane over at least 2 feet of compacted soil with very low permeability. The liner is not there because anyone believes a sheet of plastic is magical. It is one part of a defensive system. Above it sits a drainage layer, often made from gravel or synthetic drainage material, with perforated pipes running through it. The floor is graded so liquid flows toward collection points rather than forming a deep pool. And that brings us to the first major movement: water. Rain falls on the active surface. Moisture is already present in food, paper, and yard waste. As liquid passes through the buried material, it picks up dissolved and suspended substances. The result is called leachate. The safest way to manage leachate is to keep its level above the liner as low as practical and remove it. Federal design criteria call for a collection system that keeps the depth of liquid over the liner below 30 centimeters under normal conditions. The perforated pipes carry it to a sump, where pumps lift it out of the landfill. Depending on the site and the composition of the liquid, it may be sent to a wastewater treatment plant, treated on site, or managed through another permitted process. This reveals something counterintuitive. A liner without drainage would be incomplete. Even a strong barrier faces more pressure when liquid builds above it, just as water pushes harder near the bottom of a deep tank. The liner slows movement. The drainage system reduces the force trying to drive that movement. Monitoring wells around the landfill provide another layer of defense by allowing operators to compare groundwater conditions up gradient and down gradient of the site. Back inside the waste, oxygen is gradually used up. Microorganisms continue breaking down organic material under oxygen-poor conditions, producing landfill gas. The mixture varies with age and conditions, but it is typically around half methane and half carbon dioxide, with small amounts of other gases. Gas is the second major movement. It does not politely remain where it was produced. It can travel through pores in the waste and surrounding soil, follow utility trenches, or collect beneath a cover. Methane is also combustible, so larger landfills use monitoring and collection systems to control where the gas goes. Vertical wells may be drilled into completed areas of waste, while horizontal collectors can be installed as new layers are built. Blowers apply a controlled vacuum, drawing gas through a network of pipes. The balance matters. Too little suction leaves gas uncollected, too much can pull air into the landfill, disrupting the oxygen-poor conditions and increasing the risk of subsurface heating. Once collected, the gas still needs a destination. At some sites it is burned in a flare, converting methane into carbon dioxide and water. At others it fuels engines, turbines or boilers. It can also be cleaned and upgraded, so the methane can serve as a substitute for conventional natural gas. None of these paths makes the waste disappear, but each turns an uncontrolled flow into a managed one. As the active cell fills, another layer begins. The landfill grows in carefully planned stages rather than as a single chaotic pile. Temporary slopes must shed stormwater. Roads have to move as the working phase moves. Gas pipes and leachate lines must remain accessible. Survey crews track the shape of the site because every cubic yard used today is capacity that cannot be sold tomorrow. Eventually, the permitted airspace is exhausted. The trucks move elsewhere, but the engineering does not stop. In a sense, closure begins the longest part of the landfill's life. Crews reshape the final surface to drain rainfall, then install a cap. Federal minimum standards call for a low permeability infiltration layer and an erosion layer that can support plant growth, although approved alternative designs are possible. The cap must limit water entering the waste while accommodating settlement below. Drainage channels carry stormwater away. Vegetation protects soil from wind and rain, but deep-rooted plants may be avoided because roots could disturb the barrier system. The finished mound can look surprisingly ordinary. It may become open grassland, a wildlife area, a solar site, or carefully planned public space. But its future use is restricted by what lies underneath. Heavy buildings can be difficult because the ground continues to settle. Any foundation or utility that penetrates the cap could create a new path for water or gas. Now the scale of the commitment becomes clear. Under federal criteria, post-closure care normally continues for 30 years, though regulators can shorten or extend that period based on conditions. During that time, the final cover, leachate system, groundwater wells, and methane controls must be maintained and monitored. Pumps can fail, pipes can clog, soil can erode. A depression caused by settlement can collect rainwater. Closed does not mean abandoned. Our single bag may now be compressed beneath many layers of other people's ordinary lives. Most of it will not break down quickly. That is partly a consequence of the landfill's design. By limiting water and controlling air, the system favors containment over rapid decomposition. A landfill is not intended to be a giant compost pile. Its main job is to isolate material and manage the byproducts that still emerge. That distinction matters because the most impressive feature is not any single membrane, pipe or machine. It is the way the parts support one another. Compaction preserves space but creates settlement. The cap limits rain but must bend with the settling waste. The liner slows leachate while the drainage pipes remove it and monitoring wells check what happens beyond it. Gas wells collect methane, while operators continually adjust the vacuum as conditions change. So the next time a garbage truck carries a bag away, picture more than a distant mound. Picture a moving construction zone operating one small phase at a time. Picture liquid draining through gravel into buried pipes, gas drawn through wells, surveyors measuring a surface that will keep changing, and technicians maintaining equipment long after the last truck leaves. The trash is out of sight, but it has never truly disappeared. What keeps it out of mind is a system designed to control water, gas, and movement for decades. That is the hidden achievement of a modern landfill, not making waste vanish, but keeping its long afterlife predictable.